Esteemed colleagues, I would like to present a proposition of the model of temperature change description during fatigue load. The effect of temperature changes induced by fatigue loading can be used for fatigue life or fatigue limit prediction. The methods proposed so far are usually based on the rate of temperature increase in the phase A presented on this figure, or assume existence of quasi-equilibrium thermal state when the increment of temperature on the surface of the specimen is constant. However, many of our thermographic tests indicate the possibility of three cases regarding temperature changes in the phase B due to fatigue load: decrease of temperature, figure A; stable temperature, figure B; increase of temperature, figure C. The case C, named on this figure as the second type, is the most interesting for us, especially because of the often occurrence in the case of tests with 20 kHz resonance frequency in the gigacyclic range. Increase of temperature during the fatigue test were observed by us not only in the high-frequency tests. For example, we observed this in case of reverse bending of various grades of steel, uniaxial loading of aluminum alloy or ductile cast iron, or uniaxial and multiaxial loading of brass. Second assumption, often found in the methods used so far, assumes that the energetic parameter associated with the area under the temperature versus number of cycles is constant. However, our tests show that this parameter depends on the load level. Our future research directions related to tests at high load frequencies have indicated the need to develop a simple model of the temperature change description during fatigue load in the case of increase of temperature in the phase B. The proposed model was used for description of the temperature change for various metals, but in this presentation it will be shown on an example of austenitic stainless steel under reversed bending. Research results for other materials will be presented in an actually prepared larger study. The fatigue tests were carried out at 6 load levels. The main test results are presented in the table. The proposed model of the temperature change during fatigue load is a simple power function with two parameters, A and B. This is the samples of the test data estimation by the proposed model for the load level 360 megapascals, 400 and 440. There is a good agreement between the model and the experimental results for phase A and B. The model does not correctly describe phase C, where the growth of the crack and sudden increase in temperature occurs. The energetic parameter can be determined on the base of experimental data by the calculations of the area under the curve or by the model. As you can see, there is a good agreement between value of this parameter obtained by the numerically calculated area and by the model. The figures present the energetic parameter as a function of the load level. On the left figure, the total energetic parameter decreases while the load level increases. But interesting is presentation of the energetic parameter per cycle as a function of the load level on the right figure. The dissipated energy per cycle increases and consequently the parameter increases. During analysis of the test data and the model, it was found that the model parameter A and B can be presented as a function of the load level. The value of the parameter A decreases as the load level increases, and vice versa in the case of parameter B. Its value increases with the load level. Above will be used in the future to include the load level in the model. Summarizing, the proposed simple model allows estimation of the energy parameter with high compliance without the need of numerical integration of the area under the temperature change versus number of cycle curve. The error of the estimation of this parameter compared to the value determined by integration increases with the load level. The maximum value of this error for the presented example did not exceed 10%. Parameters A and B of the proposed model depend on the load level. An attempt will be made to include this dependence in the model. Total value of the energy parameter decreases while the load level increases. The energy parameter per cycle increases with the load level. The presented model will be the basis for a new thermographic method of rapid determination of the fatigue curve. Thank you for your attention.